Hi, welcome to AB Video 6.2a Part 1, Introduction to Growth and Decay. They would give you the formula. So this is an application of exponential functions. We're going to be looking at exponential growth and decay, and this is what exponential growth and decay is. It's a situation where the rate of change of a quantity is proportional to the quantity itself. Now, is proportional to means the same thing as varies directly as or is directly proportional to. So if you translate that, you have the rate of change, which is a derivative, it'll be with respect to time, of a quantity, which we'll call y, is proportional to, if you remember from Algebra 1, translates into equals k times, and the quantity is the same as that quantity, which is y. Now, what's going to happen is you're going to have a lot of problems that are going to have this same thing. Let me show you this one right here. Okay, this is from another textbook, but you'll notice it says the rate of natural increase of a population of a certain city is proportional to the population. Bacteria grown in a certain culture increases at a rate proportional to the number present. Population of a town is decreasing at a rate proportional to its size, which is the size of the population. The growth of bacteria is proportional to the number present, which is the number of bacteria. What else have we got? Sugar decomposes in water at a rate proportional to the amount still unchanged, which is proportional to the sugar that's there. So they will tell you that what you have is a situation where you have a rate of change of a quantity and it is proportional to the quantity. Now, this is a differential equation, and I'm going to solve this for you. Now, I'm going to tell you right now, once in the last 30 years have they actually asked a student in the free response to solve this particular type of differential equation that comes from exponential growth. So I wouldn't worry too much about it, but I'm going to walk you through it, which is not very difficult. It's a differential equation. We're going to separate the variables. We're going to bring the y's to one side and the t's to the other. Now remember, y and t are what we want in our final answer. Instead of y as a function of x, we want y as a function of t. K, by the way, is a constant of proportionality. That is a number, okay? So I put the y's on the left, the t's on the right. I integrate both sides. Integral of 1 over y dy is ln y. Now, this is a quantity, so I don't really need the absolute values because you're not going to have a negative number of bacteria or a negative number of people in a city. Integrating k dt gives kt plus c1. Now, what happens is if I isolate, I'm trying to solve for y, this means log base e of y equals kt plus c1, which means it becomes y equals e to the power of kt plus c1. Now, one would think we're done, but we're not. Because, and this is the tricky part that you would need to know, they actually take this expression, e to the kt plus c1, and break it up into this expression, because you got to ask yourself, when do I add exponents? I add exponents when I multiply two things with the same base. So you could see that you would add these exponents. Now the reason we do that is because e, being the constant 2.71 to the power of c1, which is just another constant, gives just another constant. So it becomes y equals c times e to the kt. Now this is the version the book has. It says that dy dt equals ky becomes y equals k times e to the ct. But I'd like to take it one step further. If you look at when time equals 0, which is the starting time, if t is 0, then k times 0 is 0, e to the 0 is 1, and 1 times c is c. So what you find out is that when you let t equal 0, that number c is actually the quantity at time 0, which makes it the initial quantity, and I prefer to write it as y equals y0 times e to the kt, because that just makes it more obvious to me that this is the initial amount. So the amount of stuff will equal the initial amount of stuff times e to the power of k, which you'll need to find that constant, of t, and you need your answer to be just in terms of y and t. So e already is a known constant. It means that you got to find y0 and k. They'll usually give you the initial amount, so all you have to do is find k, and they'll give you another initial condition. So honestly, what I'm saying to you is once you establish its exponential growth or decay, boom, right from there you can go to this. Unless they tell you they want to see that you solve that, then that's fine. So y will be the final amount, y0 is the initial amount at time t equals 0, and t will be the time. Okay, so once again, unless you're told to show the work involved in solving the differential equation, you can go directly from dy dt equals ky to y equals y0 times e to the kt. Now I just want to explore the graphs a little bit. You should know that y equals e to the x looks like this. So if I change the x-axis to the t-axis, it looks like this. And you can see how it grows very slowly and takes off like crazy. Y equals e to the 2t actually wouldn't look much different. Y equals y0 times e to the 2t. You can see here if I replace t by 0, I'll get e to the 0, which is 1. Whereas here, if I replace t by 0, I'll get e to the 0, which is 1 times y0. And of course, we're not going to be looking at negative time, and we're not going to be looking at negative quantities. So it really just becomes this first quadrant graph that starts at the point 0, y0, and is concave up and rises forever. Okay, so now let's talk about the difference between exponential growth and decay. This is an example of exponential growth because if k is positive, it should make sense to you as t gets bigger and bigger and bigger. So if you replace t by 1, 2, 3, 4, 5 hours, this becomes e to the 2, 4, 6, 8, 10 hours, and obviously 2.7 to the 2. And then you raise it to the 3, that'll be even bigger. Raise it to the 4, it'll be even bigger. So as t gets bigger, y is going to get bigger, such as this graph. As I move to the right, my y values are going up. Exponential decay will happen when the k is negative. So for example, y equals y0 times e to the negative 2t. Because now what's going to happen is y equals e to the negative 2t. If you think about it, is 1 over e to the 2t, which is 1 over e squared to the power of t. 1 over e squared, of course, is less than 1, and you know that an exponential function, if the base is less than 1, then it falls. Now again, if I replace t by 0, then e to the 0 will be 1, but if I have y equals y0 times e to the negative 2t, my initial amount will be y0, and then it'll decay. Now the interesting thing here for exponential growth, it will grow forever. I mean, if you buy 2 rabbits, then, 2 weeks later you have 3 rabbits, and then 6 weeks later you have 15 rabbits, and a month later you have 200 rabbits. I mean, if you don't get rid of any of these rabbits or have them for dinner, you're going to have thousands and thousands and millions of rabbits, as long as you keep feeding them and they don't die off. Okay, but for exponential decay, which happens with radioactive material, you'll start with a certain amount and it will decay, but it's never going to become a negative amount, so it'll approach 0 as far as when t approaches 0. So again, one more time, dy dt equals ky becomes y equals y0 times e to the kt. Y is the final amount, t is the time, y0 is the constant initial amount when t equals 0, k is the constant. You're usually given the y0 and an initial condition so that you can find the value of k, or the shortcut I've showed you where you can find the value of e to a number k. Your final equation is y equals a function of t. So let's take a situation where they tell you that the half-life of a certain radioactive material is whatever. So half-life means the number of years it takes for half the amount to decay. And they give you an example. Carbon-14 has a half-life of 5,730 years. Okay, that's what's called carbon-14 dating. Okay, now there's 2 ways to solve this. First of all, they won't tell you, but they should. Radioactive decay is an example of exponential decay. So it's dy dt equals ky, which we already know becomes y equals y0 times e to the kt. Now, what is the initial amount? Well, here's the deal. It says it takes 5,730 years for half of the amount to decay. So if you set y0 as your initial amount, you replace t by 5,730 years, you know that 5,730 years later, you will have half as much left as you started with. So if you started with y0, you'll have half as much left. Well, I can divide both sides by y0, and I get 1 half equals e to the 5730k. Now, of course, there's only one unknown in this equation, which is k. You wouldn't be able to solve it by hand. I mean, you'd have 5730k equals the ln of a half. K equals 1 over 5730 times the ln of a half, but then you'd stop. So you'd need a calculator. So you can use your calculator. It'll be an approximate. It'll be very ugly, lots of decimals. This is a better way to do it, okay? So if you were at, well, whatever. All right. So what I'm going to do is I'm going to stop here and go, look, I know that e to the 5730k is exactly equal to a half. So what I do is I take this e to the kt, I purposely replace it by e to the 5730k, which is this quantity, and raise it to the power of t over 5730. Now, the reason for that is when you have the power of a power, you multiply the exponent, the 5730s will cancel, leaving me with the famous kt. The beauty of doing it this way is this parentheses is this expression, which is exactly 1 half. Now, your equation would be just y equals whatever the initial amount is times 1 half to the t over 5730. You might remember this from Algebra 2 and P-Calc. They would give you the formula. I don't know if you ever noticed that when they talked about half-life, there'd be the number 1 half here, and that's why.